We're going to be talking about gases. And remember, when you're talking about gases, it's not a liquid. And this state we measure in the laboratory as pressure. So some of the material that you read, you may see a small p in front of different things like the CO2 and the oxygen. And it's because it's referred to as pressure, because it's not a liquid that we can physically see. It's in a different state. The first main area that this is all related to is pH. I think everybody understands pH. We've heard about it probably most of our lives and in all your science classes. And we know that an acidic compound has more hydrogens as it gets more acidic, and that a base or an alkaline has more OH components. And pH of 7.0 is considered neutral. So when you move down negatively towards 1, you're getting more and more and more hydrogen ions. And as you move up to 14, you're getting fewer hydrogens and more hydroxy. Okay? And the two, hydrogen and the hydroxy, make water. Okay, so it kind of dissipates into the two gases. The human body is not exactly a neutral pH. We have a buffering system. There are several buffering systems in the body, but the main buffering system that we're going to be getting into is carbonic acid to bicarbonate and how this affects the pH and those hydrogen ions, availability or lack of. This is carbonic acid, and if it loses a hydrogen, it becomes bicarbonate. And where did we talk about bicarbonate? Last week. It's one of the electrolytes, okay? And it's just showing you how it dissociates, but it's reversible, okay? And just to remind you, this was all on one little chart. I don't know why they stuck the hydrogen in there, but just to make sure you understood that it can react to make water. But we are looking at the carbonic acid to bicarbonate buffering system for our pH. It is considered the most important blood buffer. So it's in the bloodstream, but it goes in and out throughout the body, through all of the extracellular spaces and on into the cells. And we're talking about pressure changes. This is showing you how if you have CO2, forms the carbonic acid and then dissociates again. The same thing that we just talked about. Henderson-Hasselbalch is at least two scientists that came up with the pH formula years ago and applied it to the human body. You need to know this formula. And we're going to walk through it a little bit. And this formula is one of the reasons I have had issues with the BOC, because of your log function. You have to have a log function on your calculator if you're going to do anything with this area. And at conference week before last, I brought it up again. I said, you're telling us we have to teach log, but they're not being permitted to take it in, and they're going to get on it. So hopefully you'll be able to take these TI-30s of your own into your testing. And it has log functions on it, which we're going to do some. So I don't have enough for everybody. If you have one, it would probably be good to bring to class. But I just want you to look at this formula, but we're going to make it a little more simpler than this. So you don't have to remember it exactly like this. We're going to make a few changes. This is a constant, the alpha, times, and this should be a small p, the pressure of your carbon dioxide. It's actually equivalent to carbonic acid. Okay? So you can kind of see how total CO2 or the carbon dioxide pressure is is related to carbonic acid. The pK for the human body is a known of 6.1. So if we are able to figure this formula out, and simplified, we're going to plug in carbonic acid. So we have bicarb over carbonic acid. The log of that integer is usually 1.3-ish to add to the 6.1 to give you what a normal blood pH. So we're slightly basic, normal pH. And we have a very, very small window that the human body can function. Once we get outside that small window, then we start having problems. So this is actually what you need to know this part over here. Okay, 6.1 is a known plus the log of bicarbonate over carbonic acid. And hopefully it's 7.40. Think about gases. We're talking about oxygen and carbon dioxide transportation through the body, and you alluded a little bit back in hemo. In what area? These two components. Where do you remember oxygen and carbon dioxide in the hematology? And hemoglobin. Okay, hemoglobin carries both of them, but not at the same time. It switches them out. So it takes the CO2 away from the area, and it carries the oxygen to the area. So these are in the bloodstream, but when they get to where they need to be, they disassociate from the hemoglobin molecule. Okay, so they are moving through they cross lipid membranes. Okay, and they normally go from a high concentration to a low concentration. And this is considered diffusion. And we just talked about that, sorry. Trying to help you remember a whole different subject and how hemoglobin now is coming in to this chemistry component that we're going to be talking about. The respiratory system. It will use a long distance transportation or a short distance movement across the membranes. Okay, long distance meaning it travels through the bloodstream, and then once it gets to the cells, it quickly switches over your oxygen and your carbon dioxide. Your lungs are the respiratory component, and we understand that. They control the carbonic acid. Your kidneys control the metabolic component, which is your bicarbonate. You want to get those straight in your mind. So metabolic has to do with the renal system. We didn't get into a lot of that. We will this summer in urinalysis, with bicarbonate being moved back and forth through that system. The lungs take care of the carbonic acid. And just remember the carbonic acid, how it's related. We've got a hydrogen ion, bicarbonate, we've got CO2 here. Okay, so they're linked. So when we say respiratory, think CO2. When we say metabolic, think bicarbonate. The carbon dioxide in the blood is actually in 5 components, but there's really just 2 of them that are the majority and that we're going to be concerned with, okay? And that's the bicarbonate, which is almost all of it, and then the carbonic acid, where it's going back and forth, The rest of these, sometimes we do measure, but they are smaller, and at this point they're not that significant for our purposes. And the little t stands for total, as opposed to like this is dissolved. Okay, we have an isohydric shift. And that's what we were just talking about, that the RBCs, the hemoglobin, is related to. We've got CO2 moving out of the cells into the RBCs and oxygen from the RBCs into the tissue cells. Okay? And that's considered an isohydric shift. I want you to just remember from last week we did talk about a chloride shift. It's different, but yet it's related. Just keep it in your mind. Here, the bicarbonate moves out of the red cells and chloride moves in, okay, because they're trying to keep a balance along the way. And this is how your body is making adjustments to try to keep everything stable. So we've got CO2, which a component of is a bicarb. That's going into the RBCs. Then down here, we've got this bicarb coming out of the red cells and chloride shifting in. We're going to talk about some acid-base disorders. It does get a little confusing, but we're going to learn some real simple steps to help you kind of keep it straight. We've got 4, but it's composed of basically 4 words, okay? Metabolic, and which component did I just say was metabolic? The bicarb. And respiratory, which component is it? The CO2. And we know that acidosis means, for the human body, below 7.40. And alkalosis then would be above 7.40. So you're going to have to know some more reference intervals here to be able to determine what type of acid-base disorder we have. Okay, and we're going to kind of work through this. We classify it by the pH, obviously acidosis or alkalosis, and the origin of the problem, which is respiratory or metabolic. Okay? So if we've got a problem with our kidneys, then we're going to have a metabolic issue. If we've got a problem, these are primary. Now we can always have secondaries. We're talking about primary situations. With the lungs, it becomes a respiratory disorder. We're talking about basically 3 components: pH, bicarb, and CO2. And as I said, the body is a great regulator of itself. It has all these systems intertwined. It's going to try to compensate for the component that's out of kilter. So if I've got a problem with my renal system, my lungs are going to try to compensate to get that pH back to normal. Okay? And it goes back to that formula for the Henderson-Hasselbalch for your pH. That's how it adjusts. Okay? You've got the log of the 2 components, and if you adjust one of them, you can alter the pH. So you need to know that formula well, and it will help you understand these steps. So let's just write it up here. I guess we can use red. So what was the pH? The Henderson-Hasselbalch equation. And I'm just going to use the 6.1. I don't hear anything. The log of what? And in parentheses, it's not a math portion, I'm going to write CO2, okay, to help you remember. So if one of these is off, the other one can make an adjustment to change the pH. Okay? Just think about fractions. If you, in your dilutions, if you changed one of the numbers, the quantity, increased it or even decreased it, your total comes out differently. So this is saying when my kidneys are having a problem, they're going to change this pH. So the lungs are going to kick in and compensate for the kidneys to bring this back to where it should be. And normal is see, we only have a small window of what's normal. And our body works very hard to keep it in that small window. So as we see it changing, as the alternate component kicks in, we're going to start to see some partial compensation when this pH over here is approaching normal of 7.40, excuse me, okay? Once it reaches it, then it's considered fully compensated when it gets back to normal, okay? You have this chart in your textbook, and it has these components on it. This is showing me, okay, for metabolic, so I've got a problem with which component? The bicarbonate, because it's a metabolic problem. And this is an acidosis. Acidosis means my pH has gone down. Okay? My bicarbonate has gone down, and that caused the pH to go down. Okay? Because this fraction changed, got smaller, and it caused the pH to drop. Then the lungs are going to kick in, and they're going to drop. The CO2 is going to drop to bring this fraction back to where it needs to be. Does that make sense? If you understand the math that's going on, I know we all love math, but you know, just don't think about the log right now, and that won't confuse you. You just think about this fraction here where you've got the bicarb, the metabolic, the renal on top, and the respiratory CO2 from your lungs on the bottom. How if one goes down, it can affect your pH. And so then the other one kicks in to compensate for it. Okay? This also shows you, let's just look at the respiratory acidosis. We still got a low pH, but the respiratory component is the primary problem, and it has increased. So your bottom number went up, therefore making this a smaller number, which dropped the pH. And so then the kidneys are going to kick in and increase the bicarbonate. And then just the opposite for the other components. So, are you really confused now? Oh, we have to remember all of those? Yes. Okay. You need to be able to take a patient's blood gas readings and decide which disorder they're in. You will also learn to decide, are they partially compensated, have they become fully compensated, and that's the pH. So you almost have to have two sets of readings. I mean, you can make the best possibility. So if you're only given one set of answers, so you can't see how it's changed, then you just have to choose the best of the choices given you. But usually to determine if you've got partial compensation, you've got to have the pH before the change to know, did the pH change any? know these three things. And this will make it so much simpler. Okay? Metabolic component always follows the pH. Now we're talking about primary cause, primary origin. If I've got a problem in my renal system, my bicarb is going to cause the pH to go the same direction. It's not really follows, it's really the pH follows it, but just to make it simplify, because when we get a result, pH is always first. You look at the pH first to decide are we acidotic or alkalotic, okay? But the bicarb is going to go in the same direction as pH. So if pH is down, you would expect your bicarb to be down if it's a metabolic disorder. Okay? So if I had a pH of 7.25 and a low bicarb, can you just take a guess which of the four disorders? A low pH, so I've got an acidosis going on, and I just told you the bicarb was low. So if that's all I know, I'm going to call it a metabolic acidosis. Okay? And metabolic acidosis is the most common one that you will be seeing. So we're going to talk even more about it. The respiratory, if it is the initial cause, it is the opposite of the pH. So if you just had those three readings, and you're going to have to know what is normal, your reference intervals. If you have a high pH and a low CO2, you're going to think it's a respiratory because they're opposites. One's up and one's down. Okay? And because the pH is up, it's going to be alkalosis. Then the other party, whichever one isn't causing the problem over here, is going to start compensating. And they always follow the source of origin. Okay? So if my source of origin is my CO2, my bicarb, this one went down, my bicarb went down. My PCO2 went up, so my bicarb went up. Okay? And even up here. My bicarb is up, so my PCO2 went up. So just think about this fraction. It's trying to get it back to the same ratio that it was, which in turn affects the pH. Okay? Now, oftentimes we'll get the patient in between. You know, they're not always perfectly a metabolic acidosis when we get a specimen to test. They might be partially compensated, or it might have just started. And so, you know, it's kind of hard to put the numbers together. But eventually, they'll be clear enough that you can see. And if you know the reference intervals, then even if it's slightly out of the reference intervals, you'll be able to call these four different disorders. Okay. So you got those three rules? Have them memorized now? This is also in your textbook. When we are measuring blood gases, and not all laboratories measure blood gases anymore, we've come up with a lot of more point-of-care type testing. They do it right there in ER, or you know, the pulse ox that goes on your finger. They count on that a lot. But regularly, they are ABGs, arterial blood gases. We don't care about the venous. The arterial, because we want to measure oxygen. Now, none of this was talking about oxygen. But a true ABG, arterial blood gas, should be an arterial specimen, and they generally get it from the wrist. And it is cherry red because it's full of oxygen, we hope. Okay? So this is the parameters that you're generally going to see, at least these, on a blood gas analysis. And you need to start getting comfortable with them. However, if you think back to methods, and we're going to talk some more about methods, the electrodes are what we're measuring. We're using ISEs basically to measure. Only 3 are directly measured. Everything else is calculated. Okay, so we're only going to learn those 3 measuring devices. For pH, PCO2, and PO2. And you need to know these reference intervals. Just look at the numbers, okay? Your pH, you're just going to have to know it. It's 7.40 plus or minus 0.5, okay? 735 to 745. You got to know that. And just right outside that, changes start occurring that are significant. Look at this CO2. Does that look familiar? Okay, so that'll help you remember the CO2. If you got the pH, just remember drop the 7 decimal, you got the PCO2, what's normal. Okay, now oxygen's a little bit harder, but just think, I want to breathe at 100% normal, okay? So it's around 100 is what we're going for oxygen, okay? Notice these are millimeters of mercury, okay? So sometimes you may have to find out what the barometric pressure is, because that does affect. Remember from hemo and that hemoglobin? People that were in a higher altitude, didn't they have to compensate? So barometric pressure does make a difference. And generally you had to call wherever the source was, and it's usually the airport or the weather people, to get what is the corrected barometric pressure right now, because I don't think it changes as bad here as where I came from. We were in a valley and it dropped drastically from time to time, and we'd have to call just to as part of our maintenance checkup to make sure our instrument was reading correctly. Did it adjust as the conditions that we're in changed for barometric pressure? Okay, because we're measuring pressure of these gases. Now this bicarb and this total CO2, they're going to be calculated. Okay, so if you only get this out of this part, only 3 are directly measured. Everything else is calculated. And you won't have to know those formulas, but they kind of go with this. Now I want you to look at the difference, okay? This is the bicarb component, and that's about what we had for reference intervals last week on our ISEs. Yes? You got those memorized? Yeah, you will. Okay, about 20. And that'll vary a little bit from facility to facility, from region. And then total CO2 is about 4 higher. So that tells me 20 parts of the 24 are the bicarb. So most of your CO2 is bicarb. Now some facilities measure bicarb for their electrolytes, and other facilities will measure CO2. So you're going to have to realize what you're looking at and which reference interval is applicable on your electrolytes. Okay? Our instrument in here did not measure bicarb. It just had the 3 main ones. Then we would have done a CO2, a total CO2, in the wet chemistry portion. Okay, so this is in your textbook for you to refer to and get memorized. Now we're going to do some interpretations. When you get your answers, now I did say that it's either a respiratory or metabolic origin. That's where the problem is supposed to have started. But when we read them, we see pH first. So we're going to look at the pH of our patient answers. We know what the normal is supposed to be. So if we see a pH elevated above this 7.45, we're going to think alkalosis. And if we see a pH below the 7.35, we're going to know this is an acidotic situation. So there's half of your disorder. Okay? Then you're going to look at, and actually 2 and 3 you can reverse, but usually the PCO2 is the next thing you're going to be seeing on the report. You're going to look at it, and I know that it's 35 to 45, and I don't know why they decided 35 and 48 here, but if my PCO2 is elevated, I'm going to say, ha, I got a respiratory problem going on. Or if my PCO2 is below the normal, I've got a respiratory component going on. That slide before, I said if you had a respiratory problem, your PCO2 follows or is opposite your pH. Okay, so this one's up, and this is saying this one's down. Okay, so if that's what I should see if I have a respiratory problem going on. Whereas this one's down, I should expect my pH to be up. That is if the lungs are your problem, primary problem. But maybe they're not. Maybe it's nice and normal. You know, maybe it is 40, right on the nose. Then I'm going to look at my bicarbonate. And if it is greater than, this is the bicarbonate normal, not the CO2 total that was on the bottom. It's over 22, I'm going to think, okay, I've got this elevated, my pH is elevated, I've got a metabolic alkalosis, and vice versa. Metabolic acidosis is what you're going to be seeing most. You're going to have a low bicarb and a low pH. This is when the disorder just is beginning. Body hasn't adjusted yet. One or the other. Okay? The other one would be in the normal area. But you don't know when you're going to get your specimen or see your results from your patient. They come in, they've been in distress for a while usually, unless they've been in an accident. And then they come in. Their body is going to start compensating at some point, unless it's a really bad accident and they can't. But then the other component will start to change. And the other component's going to go which way? It's going to go with the origin. Okay? Now we're going to talk about these four. Okay, and it's going to get a little confusing, but go home tonight, memorize this formula over here, and the three little rules to help you put these four disorders in order. So I'm looking at metabolic acidosis. I know my pH has gone down below 7.35, and it's metabolic, so my bicarb follows the pH, so it's gone down also. So it's below 18 in this case. And at first I'll have a normal PCO2, but eventually, which way is that PCO2 going to go? It's going to follow the bicarb. And another thing, remember bicarbs were connected to electrolytes? So that anion gap that I told you we never really look at, it's going to change because of the bicarb amount. Some things that can cause this. Metabolic acidosis is the most common acid-base disorder you're going to see. You're going to have somebody present maybe in the ER having struggle breathing, maybe in and out of consciousness. The most often cause of this is diabetic ketoacidosis. Okay. They are going to have impaired renal, metabolic, okay. They're going to end up with surplus acid, that's our hydrogen ion, giving us the acidosis. You can also see this if you have extreme diarrhea. And some of the things you're going to see with it is an increased anion gap, and this is listing things that can affect an anion gap. I threw this out here because it was listed somewhere. I don't know if people are still utilizing this, but just file this away. Not that I'm going to ask you a question, but maybe the BOC would. MedPiles is a acronym for these elements that apply to metabolic acidosis. MedPiles. You can see several of them are a type of a drug. Methanol, ethanol, paraaldehyde, salicylate. Okay, here is diabetic ketoacidosis. And if you go back to page 148 under our carb lecture, it kind of starts spelling this out for you, and then you can put it together with what is listed under your metabolic acidosis paragraph on 296. But on 148, I think it's on the right column. Did you find it? Okay. And it's going to tell you what is happening here. Remember back on your metabolic, or excuse me, your diabetic, what is happening to them? Okay. Insulin is going to do what with the glucose? Okay, so this glucose is not going into the cells. The cells are starved. They want some energy sources. So they're going to get it. Read that a little bit and see if you can figure out where they're going to get it. On page 148. So, yes, from your lipids. Now, this is not usually your first stage type 2 people because they're usually obese. This is more for your type 1, although your type 2s eventually will get there. These people tend to lose weight because their body's going after the fats to find a fuel. Okay, the fatty acids break down, and in that process, they have excess hydrogen ions floating around, and they're tied to different ketones, which we haven't talked about those, but we will in urines there again. There's different ketones, but they are acids. So we've got these extra hydrogen ions floating around because of that, and they're going to grab onto the bicarbs and form carbonic acid. So that reduces the bicarb. That's a renal entity. That's the beginning of your problem. Well, it's not really, but the beginning of the acidosis problem. Then this carbonic acid, it's going to break down to, do you know what this will make? And water. And the CO2 is going to get blown out in the lungs. Okay? So this reduction in the bicarbonate has resulted in a lower pH because over here it's messed up this calculation over here. Okay? So this is diabetic ketoacidosis in its simplest form. And it's all because there's no insulin or not nearly enough insulin to get that energy source from your carbs into the cells. So they got to go find it somewhere else. So they'll have fat breakdown. And this is like waste. The ketones are the waste from this fat. A person who is starving also experiences this. If people that go on extreme dieting will start spilling ketones, and they possibly could fall into this category. Or if you have some other primary condition that causes you to be in a starvation state, you can fall into this category, okay? These are some of the tests that we would be looking at, the doctors would be looking at, besides their blood gases, to help them decide what's going on with this patient. That's a renal problem. The lungs are going to kick in to try to compensate. Okay, and there was a scientist or a physician, I'm not sure what he was, German, I'm sure, Kussmaul, came up with this symptom that he noticed his patients were having, and they called it Kussmaul breathing. And they often present this way. And I found it a very good Can you hear it? He's almost comatose. You can smell it out of his mouth. Okay? Hyperventilating. The lungs are trying to compensate for this loss of bicarb from the renal system. Okay? Does that kind of help you put the pieces together? Metabolic acidosis, think DKA, because that's the most common one that you'll see. And it's usually, well, I shouldn't say usually, because we're seeing it more and more and more, but often a younger person who has not been diagnosed, they just switched over to become a type 1 diabetic. And they're almost comatose, so they can't tell you, so you know they're not breathing that way on their own. Okay, you know, we can make ourselves hyperventilate, but this person isn't conscious, so it's very mind-boggling, and that's how they'll present in the ER. You might be the one to go down there to collect some blood or something, and you will actually see some of these patients. Hyperventilation is the compensatory mechanism for metabolic acidosis. Okay? Moving on to the next one, metabolic alkalosis. Now our pH is going to go up. Okay, it's still being caused by the renal system, the bicarbonate, but the pH is going to go up. So I know because it's gone up, the cause was an increase in bicarbonate. Okay? Bicarbonate is related to the other electrolytes, so we're going to see some changes there. You don't know much about calcium yet, but it's right in there with it. It's an ion. And some of the things you're going to see, well, you know, we have a lot of conditions that cause confusion or even coma. We're going to see some neuromuscular irritability, or tetany is related to your calcium. And this helps you put these pieces together. Okay, still thinking about an increase in bicarb. Okay, we have a loss of hydrogen in our body fluids, which could be from something like vomiting. Or maybe they have a primary condition of renal failure to begin with, okay? So your diabetic patients eventually do have renal issues, and you'll start seeing it more and more the further their condition progresses. And I don't know if you remember in our electrolyte lecture, we talked about potassium changes place, crosses membranes with hydrogen. Okay? These hydrogens are coming out and the potassium is going in the cells, so they become hypokalemic. They've lost potassium in the bloodstream, in the serum. Okay? If you have a overuse of diuretics, you're going to start seeing in a lot of renal issues, which this is one of those. Quite a few different things there. Okay? And how are we going to compensate? We have an increase in bicarb, increase in pH. How are we going to compensate? Increase or decrease? We're going to increase our CO2. And how are we going to do that? We're not going to blow it off. The Kuzma was blowing off excessive, trying to get rid of it, to drop it. This person is not trying to drop it. It's trying to retain that CO2 because this one went up, so we want the bottom one to go up. So we don't blow it off. So they hypoventilate to compensate for it. Okay? We're not going to get to the rest of it. We've got 2 down, okay? Now, respiratory acidosis. The CO2 in our lungs is going to cause a problem. And remember what we said about the respiratory component, the CO2? It is the opposite of your pH. So I'm going to see a decrease in my pH, an increase in this CO2 component. This is caused by hypoventilation. Okay? The other one was compensated. So the hypoventilation is the problem now. It's not fixing it, it's causing it. Make sense? I'm retaining the CO2. There's something wrong with my respiratory system. I'm not blowing off that CO2 that's been accumulating because I'm broke. Something's not functioning like it's supposed to. So I'm retaining the CO2. Hence, it's a respiratory component and it's going to drop the pH. So, how are we going to fix it? Oh, a whole bunch of causes. You're going to see a lot of people in COPD. It seems to be, I think it's increasing in our nation, but I think it's also a result of our poor health. But a lot of these are, respiratory, airway problems. But you can always have some other condition that creates that, because we're all connected and related. Let's see what the next one says. The compensation. That's where I was going. Okay, what did I say? This is respiratory acidosis. I have a low pH and a high, which component? CO2, because my lungs are causing it. They're holding on to the CO2, hypoventilating to keep it. And I'm going to compensate by retaining bicarb. because the compensation follows the origin. I got too much CO2. I'm going to hold on to that bicarb. Now think about it. When I've got a metabolic problem, the quick fix is change my respirations. Hyper or hypoventilate. That's the compensation. And that's a pretty quick fix. Well, when I've got to get my kidneys involved, it's going to take a little longer for that blood to be cycling and start changing the components in the blood. So when you have a respiratory condition, it takes longer before you start seeing that compensation take hold. Okay? And because of your bicarb, you're going to see a shift in your sodium also. Okay, is this the last one? Yes. Number 4, okay, it's another respiratory component. Got some problems with my lungs, and this is alkalosis, so I know my pH is going to be elevated. And the respiratory component is always opposite, so I'm going to have a reduction in my CO2. And how can I get a reduction in my CO2? Hyperventilate. This is the cause. Okay, so whenever you see hyper and hypoventilation, it causes respiratory problems, but it compensates for kidney problems. Okay? So just think about what you're looking at, your condition, when you go to answer those questions. Okay? And it stems back to this equation. If you got this equation, it makes common sense. Okay? But you're going to have to stop and think about what is the scenario, what's happening, and plug in into your formula and think about what's going which way. And here's some causes of this respiratory alkalosis. Looky there, we got high altitude there. People that have congestive heart failure, they start filling up with all this surplus food, so that, you know, that's the cause, but their lungs can't function. They can't pump like they're supposed to. And obviously anything to do with the red cells is going to affect your respiratory, right? But then we get often some drugs involved. We used to have a lot of, does everybody know what salicylate is? Aspirin. We used to have lots of salicylate overdoses. It's very, very easy access. Then they've gone to acetaminophen because it's easy access, and you know, they said it doesn't hurt you like salicylate, so people sometimes unintentionally take too much of it. But we used to see a lot of salicylate intoxication that you're probably not going to be seeing so much of. And you can relate to this one. Have you got to your sepsis yet? You will. So think about respiratory alkalosis, okay? Oh, and we all know somebody that fits here, right? And what do? They get all excited, throw themselves in a, well, okay, stopped working here. You can't go backwards. So we didn't talk about the compensation. We've got a respiratory alkalosis. So what's going to happen for compensation? The renal system's going to do what? I've got the CO2 is up or down. Okay, this is up, so this is down. So what's going to happen to the bicarb to try to compensate? It's used up. Okay.